Have you ever thought about what really makes up the water in your glass, the sugar in your tea, or even the oxygen you're breathing right now? At the tiniest level, all of these are made of molecules, combinations of atoms that stick together tightly to behave as a single unit. By definition, a molecule is a group of two or more atoms chemically bonded together. These atoms can be of the same element or of different elements. For example, oxygen gas is made of two oxygen atoms joined together, that's O2. Water, on the other hand, is made from two hydrogen atoms and one oxygen atom, that's H₂O. So, a molecule is the smallest part of a substance that retains all its chemical properties and can exist independently in nature. Let's now look at molecules formed from the same element called molecules of elements. Some elements, like helium or argon, exist as monoatomic molecules, that means they float around as single atoms. Others, like oxygen, hydrogen, nitrogen, and chlorine, are diatomic, they always travel in pairs. For instance, oxygen is written as O2, hydrogen as H2. And some elements go even further. Ozone is made of three oxygen atoms, we write that as O3. Sulfur can form long chains, making it polyatomic. This number of atoms in a molecule of an element is called its atomicity. For example, helium is monoatomic, oxygen is diatomic. Sulfur is polyatomic. Now let's move from elements to compounds. When atoms of different elements combine, they form molecules of compounds, and these are everywhere around us. Let's take some classic examples. Water, H₂O, is made of two hydrogen atoms and one oxygen atom. Ammonia, NH3, has one nitrogen atom and three hydrogen atoms. Carbon dioxide, CO₂, contains one carbon and two oxygen atoms. These combinations always happen in fixed ratios, so no matter where water comes from, it will always be H₂O. This consistency in chemical makeup is due to the law of constant proportions, and it helps us write accurate chemical formulas and predict reactions. Let's explore how we determine the number of atoms in a compound by comparing mass ratios. For example, in water, the elements hydrogen and oxygen combine in the ratio 1:8 by mass. Now look at their atomic masses. Hydrogen has a mass of 1 unit. Oxygen has a mass of 16 units. So we calculate mass ratio for hydrogen equals 1 divided by 1, mass ratio for oxygen equals 8 divided by 16. This gives us the simplest ratio equals to 2:1. That's why water is H₂O, two hydrogen atoms and one oxygen atom. These simple ratios form the foundation for writing molecular formulas and understanding compound structure. Now, not all chemical species are neutral like molecules, some carry a charge. These are called ions. An ion is an atom or a group of atoms that has lost or gained electrons. If it loses electrons, it becomes positively charged, we call it a cation. Example, sodium ion, written as Na+. If it gains electrons, it becomes negatively charged, we call it an anion. Example, chloride ion, written as Cl-. These ions are the building blocks of ionic compounds like salt. In sodium chloride or NaCl, a sodium cation and a chloride anion come together due to opposite charges. This attraction forms a stable ionic bond, just like a magnet sticking to a fridge. Just like molecular compounds, ionic compounds also form in fixed mass ratios. Let's look at some examples. In calcium oxide, CaO, calcium and oxygen combine in a 5:2 mass ratio. In magnesium sulfide, MgS, the ratio is 3:4. In sodium chloride, NaCl, sodium and chlorine combine in a 23:35.5 mass ratio. These ratios remain the same no matter how much compound you take. That's the beauty of chemical laws at work. Ionic compounds are held together by electrostatic forces, and their fixed composition makes them reliable for industrial and biological applications. Let's quickly revise what we've learned about molecules and ions. Molecules are made of two or more atoms chemically bonded together, and they can be made of the same or different elements. We saw that molecules of elements like oxygen exist as O2, while compounds like water exist as H₂O. We also explored the concept of atomicity, mass ratios, and chemical formulas. Then we entered the world of ions charged particles like Na and Cl- and saw how they form ionic compounds like salt. So whether it's sugar, air, or even the soap we use, everything is built from molecules and ions interacting at the atomic level. I hope this session helped you connect those textbook formulas to the world around you, where chemistry isn't just a subject, but a living process. See you in the next class, where we uncover even more secrets of matter.